document of my lecture on the Canvas, so you can access it in the files. Okay. So last time we were doing this. Okay. So we did a circuit with the inductor, and we tried to see that how it will behave and how can we calculate the current. But we also described the exponential form of the complex voltage and the current. So we will see how it will work with us today. Okay. This example 8.6. So if we have this circuit, V is equals to Ri, and then we can say the voltage across this circuit will be Ri of t. And if we apply the complex voltage rule, we can also say that if Vm is like this, theta I, and as we assume that both have the same angular frequencies, we can just write it like this. Okay, and so if we are describing it in the bold form, we are including what you should say, the phasor in it. So we are saying that the phase is in this exponent, and which will be equal to here, if we are expressing it in the phasor form, it is actually equal to V bold is equal to Vm Ej theta V, and I bold is equal to IMEJ theta I. And then if we express it in this form, we are saying here that theta V is equals to theta I, because there is no difference in both of them. So when we are expressing it in this form, we can draw its phasor like this. This is a real part, this is an imaginary part. We don't know what theta is, but if it is some theta here, that will be theta V is equals to theta I, where your V and I have the same angle. Now, when we are plotting both of them in the sinusoidal form, they have both same frequency, and if this is sine, they will follow the same, what you should say, crossings. Their amplitudes can be different, but their phase cannot be different. So if theta V is equals to theta I, then maybe this, and if it is starting from 0, so this should be in the real time, or on the x-axis. But if it has some angle, they both can start from here, showing that they have the same angle. So that's the circuit with the resistor. So in the phasor form, you can see that if we have the resistor circuit, it may not be what you should say, having a phase difference in it, right? So if we try to solve a problem in the phasor form, giving it a sinusoidal input, we will see that if this is example 8.6, we are seeing that our V of t is equal to 24 cos 377t plus 75 degrees, okay? And this voltage is applied to a resistor, which is up in the circuit. And then if this is the resistor's value is 6 ohm, if resistor value is 6 ohm, R is equals to 6 ohm, then we have to find resultant current. Okay, so how we will solve this? They said that they have the same what you should say, omega, or the frequency, so we can write it in the phasor form. So when we will write it in the phasor form, it will be equal to 2475, right? And if we try to solve the I, that will be equal to V is equals to IR. So V over R, which will be equal to 2475 by 6 ohms. Because because resistor does not have any phase in it, its phase is 0. So we can just write it like this, 475. So in that way, if we plot its phasor diagram, so we know the voltage making 75-degree angle with the real axis. So this is 75 of the voltage, and the voltage magnitude is 24. Now the current is also making the 45 angle. So the current is also in this angle, but its magnitude is of course lesser. So which makes it 4. So this is the current. This is, sorry, imaginary part, so don't confuse it with the current. So current and voltage phasor is on the same axis, but their magnitudes are different. Sounds good? Do you understand what I'm saying?
Yes.
Okay. So but now if we have an element that has the frequency dependency in it, then our scenario will change. So that element will be inductor or capacitor. So if we have inductor or capacitor in them, in the circuit, then our scenario will be changed. So let's see how it will affect our phasor, how it will affect our overall circuit. We have seen it before, but we want to see it again. So let's see. So if this is our inductor, and this is our current, V of t is equal to L di by dt. So this is the voltage current relationship of the inductor in the inductor, and where L is the form of inductor. And yes. So we don't know now why we are describing it like this. We don't know that what is here. We actually know this, that the circuit contains inductor in it. So we are just trying to find the voltage current relationship of inductor, considering that inductor is in the circuit. So we are saying that Vm Ej omega t plus theta v is equal to L d I over dt. So we can just write it like this first, L di by dt, where I has its own angle j omega t plus theta I. So we have defined theta v and theta I in the separate notation so that we can see the difference between them. So when we try to solve this circuit, we will come across like that. So because we are not writing a KVL equation, we are just saying that voltage is equal to, in the circuit, we don't know here what it is. Voltage V of t is equal to L di by dt. So we are just trying to find the voltage current relationship if the inductor is there. So I'm saying here, if I'm taking the derivative, I'm saying Li m Ej omega t plus theta I will be there. Now, if I'm writing it in the phasor form, if I'm writing in the phasor form, I will see that if my omegas are same, so I can get rid of them. I can just write it in this form. Right? But the difference with the resistor circuit is that I have J in it. And multiple times using Euler's identity, we have defined that J is actually cos 90 plus J sine 90. So when we write this in this form, cos 90 plus J sine 90 is actually equals to J, which means that the angle is 90 degrees if you have a J in your circuit. So let me see what Euler's identity we have defined before. So Euler's identity was Ej theta is equals to cos theta plus J sine theta. So if you have Ej 90, so you can write it as cos 90 plus J sine 90, where Ej 90 is equals to J, which makes theta due to J is 90 degrees. So which means that if I just replace this here, so this is not angle, this is L. So I can write this in this form. So which makes theta V and theta I relationship clear, which makes it theta V is equals to theta I plus 90 degrees. So what it suggests that who is leading what? Is that current is leading or is that the voltage is leading?
Current's leading.
Okay, why?
Because it has the additional angle.
Yes, but when I am adding additional angle, it is equal to the voltage theta, right? So let's draw it and then we will see, okay? So if I draw the phasor of it.
Professor.
Yeah.
I've been trying to submit my assignment through Canvas, but every time I click submit, it says submit failed. Please try again.
Yeah, maybe it's because that it's past 15 minutes. Oh, no, 10:15. So you can email me, okay?
Okay, thank you.
Thank you. Okay. Theta V is equals to theta I plus 90 degree. What I was saying is, so if someone else has a problem, please email me the assignment, okay? Yeah. So what I was saying is that relationship between theta V and theta I is 90 degree. By leading, we means who is coming first or who has the angle greater angle at that time in the positive sense. So let's see if theta I is 0 here. Let's say if current is 0 here, we don't know what current's angle is, but let's say that theta I is 0, then theta V is 90 degrees. So this will be theta V. So theta V is actually leading theta I in the phasor diagram, which means that voltage is leading current, which actually solves our inductor thing. Like we say, Ali, the Iceman, I don't know you were there in the lab or not, but this is that in the inductor circuit, voltage always leads the current. So if we draw this in this exponential form, we should get something like that, that if this is your current, this must be your voltage, where your voltage has the maximum value at 0 and 0 value when the current is maximum. So that means that the angle between them will be 90 degrees. So voltage is occurring first and current is occurring later if the inductor is there. So that's the relationship between voltage and current if inductor is in the circuit. Similarly, I'll just quickly talk about an example that we have done here, that if this is V of t 12 cos 377t plus 20 degrees, and it's applied to 20 millihenry, some circuit there. So this V of t is this thing, and it's applied to 20 millihenry. Then if I try to find I, so my I should be, because V is equals to j omega Li here, if you see here, Vm is equals to j omega Li. So that will become V over j omega L, okay? And V, if I write it in the phasor form, is what? 12, 20 degrees, but j omega L is j into 2 pi f into L, 20 millihenries. So it will become 12, 20 degree, which will be 2 into pi into 377 into j into 20 millihenry, and it will become 1.59, but I need to deal with angle first. So this is j, okay? And I know that j is actually what? It's actually angle 90 degree, okay? So I can just write it 1.59 20 degree minus 90 degree. This will be 1.59 minus 70 degree. So if I draw a phasor diagram, so I know that V of t is at angle 20 degree, right? So that will be somewhere here. That will be my voltage with the 20 degree. But my current is at minus 70 degree. So it should be somewhere here. That's 70 degree. And the difference between them should be 90 degree. Sounds good?
Yeah, that makes sense.
Okay, so that's what you need to remember, that in phasor form, the relationship that we have found out between voltage and current is, if the inductor is there, it's not V is equals to IL, like V is equals to IR. It's actually V is equals to J omega Li, because our reactance is J omega L, and which makes it dependent on frequency and the phase, that is at 90 degrees. So that's the difference that, with respect to resistance value. So that's very important to learn, that how our capacitor's voltage current relationship will behave. So let's see. With capacitor in the circuit. So if I have capacitor in the circuit, this will be my V of t. And I know in case of capacitor, I of t is equals to C dV over dt. And in this case, if I write like that, it will become Im. So from where these expressions come from, like V of t and L, di of di over dt, we will learn that. But first we are doing the phasor thing, and then afterwards we will learn how this expression across inductor and capacitor comes. So Im, if I write it in terms of phasor, it will become like this. Okay, and similarly, if I will take the derivative of this, it will become J omega C Vm Ej omega t plus theta V, and Im Ej omega t plus theta I. Again, the omegas are same. I can get rid of that, and I can just write it J theta I is equals to J omega C Vm Ej theta V. Now, you can see that I can also write this in this form. They both are the same thing. Okay, so they both are the same forms, phasor forms. This one is little bit elaborated form, and this one is just dealing with the angle in the simple polar form. So they both are same. Okay, so when I'm seeing this, let's see, I'm dealing with this. So I'm saying I am voltage current relationship is this. So now if you see, if I replace like that before, this will become EJ 90, EJ theta V, omega C Vm, EJ theta V plus 90, and Im EJ theta I. So this makes theta I is equal to theta V plus 90. So it is opposite of inductor. Why? Because in this case, instead of voltage, current is leading. So if in this case, I am drawing the phasor diagram and my theta V is somewhere here, I don't know what theta V is, then my theta I will be at 90 degree phase difference, and it should be here. Similarly, if I make its sinusoidal waveform and my theta I is somewhere here, sorry, theta V is somewhere here, then my theta I should be, or my voltage signal should be this. So this is what voltage signal, and this is current, which is exactly opposite tell inductor. If you see here, here my voltage is leading, and here my current is leading. So that's the difference. But we will see how much more difference this will create when they both will be in the circuit, okay? We will see in the short time. But we need to understand that inductor and capacitors are posing a difference of 90 degrees to each other. Voltage and current are posing difference of 90 degrees to each other in the presence of capacitor and inductor. So let's try to solve an example regarding that. So the example says that voltage V of t is 100 cos 314t plus 15 degrees. And capacitor is 100 microfarad. Okay, so I need to find the voltage current relationship, and I know the relationship between them is I is equals to j omega c v, where this is bold. Bold means that it has phasor in it, and I can just write it in terms of phasor, and this will be I. No, not bold this time. So this will be I am theta I j omega c v theta v in it. So like that. But if I'm trying to find out I can just write it j. What is my omega here?
314.
314. And omega c v. So my v is 100. And what is my theta v here? What is the angle of voltage?
15.
15 degrees. So my I will be j. This multiple of this is 3.14, 15 degrees. So what should I do now? I will add 90 degree in it because of j. So it will become 105 degrees. So when I will draw a phasor, I will draw voltage at 15 degrees and current at 105 degrees. Okay, make sense?
Yeah.
Okay. So now we are at very interesting point here to define impedance and admittance. Okay. We all already, I mean, know it, but we have not officially defined it. So let's define it first. So impedance and admittance. So we know impedance is defined as the impedance is like resistance in the DC circuit. So it's like in the DC circuit, you know that resistance is voltage divided by current. Similarly, in AC circuit, impedance is defined as ratio of phasor voltage to the phasor current, or AC voltage to AC current. It's same. But if I just write it like this and draw a circuit, if this is your AC voltage source, and then this will be your AC current source, you will have this equivalent resistance, if this is your, or sorry, not resistance, impedance. Why I cannot say a resistance? Because impedance can have a reactance in it. So that's why I cannot just say the resistance, it's an impedance. So if the equivalent impedance is Z with an angle theta Z, then our voltage source will be V theta V and I am theta I. Now, if I just define this in terms of Ohm's law, then I should be writing this in this form, where they all are bold. Like this. So, and I can write this as theta I. So which makes it Vm over Im theta V minus theta I. So that will be my impedance. I think we have done this in the previous, 2 examples, but we should be able to define it. And this was Z theta Z for us. So that's what the mathematical expression is. And as our impedances are dependent on frequencies, we can also write this like that. We know that resistance is not defined dependent on the frequency, but the overall impedance is a function of omega. And when I'm writing it, I can just also write this as this. And where I know that Z is R square plus X square, the magnitude of Z, and its angle is theta Z is tan inverse X over R. Okay, which makes this as R is equals to, okay, so if you have X here and R here, and this is your theta Z, this will be your Z, and then your R will be what? Z cos theta Z. Sounds good? Because this is a base, right?
Right. Yeah.
So this is R by Z, which will be cos theta Z, and similarly X by Z will be sine theta Z. So that's why you are writing X is equals to Z times sine theta Z. Okay, so this is an important result, but we want to relate impedance to admittance as well. We know that admittance is actually what it's the inverse of impedance or reciprocal of impedance. So when we say admittance, it's actually Y is equals to 1 by Z. So another form of defining it is G plus JB, where G is and B is, this is our conductance, and this is our susceptance. The basic, point is that it's inverse of impedance. So if I'm writing it as like this, how can I make sense of this and this? Okay, so I will try to do this. So my G will be so this is the relationship of G with resistance and reactance, and B with reactance and resistance. Similarly, you can try to find the opposite of this, and this should be the same. So that's how we can, find the relationship between them. And one more thing is here that we need to define. I mean, we need to write it in the tabular form, that I know in AC circuits or in phasor form, my R, what should I see? Okay. So if this is my passive element, and this is impedance. Okay. So if there is only resistor in the circuit, passive element is resistor, my impedance will be only R, because plus JX, this will be 0. So it will be Z is equals to R. If I have L in the circuit, what it should be? It should be, because I saw that my V is equals to J omega Li when there was only L in the circuit. So my Z is equals to J omega L. Make sense?
Yeah.
If this is C, and I saw that I is equal to J omega C V, that's what I saw. So my Z will be 1 over J omega C, or minus J omega over omega C. So that's the summary of that. If there is a passive element in the circuit, how I should be getting the impedance. Okay. Similarly, I should be able to write the admittance of this as well. Okay. So let me see. So if this is passive element is R, my admittance is 1 by R. Okay. If my passive element is L, my admittance will be 1 by J omega L, or minus J over omega L. Similarly, if my passive element is C in the circuit, this would be, admittance will be J omega C, because it's the inverse of impedance. Right? Sounds good?
Yep.
Anthony Rosso, you think it's fine? You're here? Thomas, you think it's good?
Yeah, it looks good.
Okay. Okay, so that's what we were seeing. The trend of impedance and admittance. Okay. So we have 5 minutes. Can we do that or not? I'm not sure. Let me start it and then we will see. Okay. Okay. So there is an example I want to do. That is example 8.9. So I am spending a little bit time on this chapter because I think that this chapter is very important for your all the basics of complex circuits like AC circuits. So that's why. Okay, so this is this circuit you have. R is equals to 25 ohms, L is equals to 20 millihenry, and C is equals to 50 microfarad. You have the circuit in which you have all of them. And this is your I of t, and this is your V of t. So what you have to do is, you are given a voltage source and the frequency, and you have to find the impedance and the current as well, I think, yes. So let's see. So your voltage is 50 cos omega t plus 30 degrees, where your omega is 60, and they said that compare your answers when your omega is 400 hertz. So it means that when you change the frequency, what will be its effect on your circuit? So first we want to find, we cannot deal AC circuit in terms of R, L, and C, because just about like before, we define the relationship in terms of impedance. So we have to convert all of them into impedance form. So which makes it Z is equals to R, which is 25 ohms, ZR, okay? I'm not just defining because it has reactance in it. So it is, it cannot be just defined as R right now. Then ZL is J omega L, where it will be 2 pi into 60 into 20 millihenry. And that is equal to J 7.54 ohms. Similarly, ZC is 1 over J omega C, which will be 1 over J into 2 pi into 60, not degree, it should not be degree, it's 60 hertz. Into 50 microfarad, that's equal to 1 over J into 53.05. Now, if you want to make J up, it will be minus J 53.05. So your total impedance is of this circuit is Z is equals to ZR plus ZL plus ZC, which makes it 25 plus J 7.54 minus J 53.05, which makes it 25 minus J 45.51 ohms. Now, the very, very important point here is that you have seen that if there is an inductor, your reactance will be positive. And if there is a capacitor, your reactance will be negative. But in the overall circuit, if you see that the reactance has a negative in it, you will say that overall effect of reactance is capacitive, because capacitor is dominating the inductor part, right? Because inductor part is small and capacitor part is large. That's why it is showing you negative reactance. But if you are seeing here, like somewhere here, it's like 25 plus J50, then this has the reactance effect is inductive. So that's very important to understand, that when your complex part is negative, your circuit has a capacitive effect. When your complex part is positive, your circuit has an inductive effect. So I think I will stop here and we will do rest of the example later. But that's what we need to understand about this chapter. And I think it's a very small portion of this is left, and next time we will start the new chapter as well. Okay, thank you very much.
Thank you. Have a good weekend.
Thank
Have a
you.
good weekend,
Thank
Professor.
you.
You too.
Have a good week.
Bye. Thank you.